Hello and welcome to question 9. In this question, it's about complex numbers, but the first part has nothing to do with it. It's just polynomials. So part 1 wants us to show that if I have a cubic polynomial that looks like this, it can be changed to another cubic polynomial that has no square terms, which is quite interesting. There's a cube term, there's a linear term, and a constant, but has no square terms. If you use the substitution x equals to y minus p over 3. So this is the substitution we're going to make. Okay, and the constant term is some alpha, where we have to find out what it is. That is part 1. Okay, so I'm going to go ahead and make the substitution. This is the equation given to us, the original cubic, the one with cube, square, and linear terms. Every time I see an x, I will replace it with y minus p over 3. So this is my x cubed, x squared, and x fully replaced. So this is where you have to be very careful with your expansion, right? So you can do a quick check and see whether you got these terms when you have fully expanded out the cube square, okay, and also multiplying this in. Ultimately, this will be the answer. You get a cube term, you get a linear term multiplied by 2p squared over 3, okay, and then this is your constant term, q minus 7 over 27p cubed, and that is the answer for part 1. Okay, now part 2 says that if you have some polynomial over here, okay, and the interesting thing is this polynomial has no square terms. Okay, so this polynomial here is given to have a root of negative 3i. If that is the case, can you find out the other two roots? So what I can do is I can call this polynomial f of y, okay, and then I can say that f of y is equals to some quadratic in y multiplied by y plus 3i, because y plus 3i will represent the root negative 3i. Okay, so how do I find out what the quadratic is? I can do long division. Okay, so let's do a quick revision on long division over here. If I take the cubic that I have, y cubed plus 6y minus 9i divided by this, how do I start? Now, you always want to focus on the first term or the leftmost term. In this case, I have a y cube. How do I resolve the y cube? What I can do is I can multiply by y squared. Okay, when I take y squared and multiply by y, that will give me a y cube. Okay, and then next, this y squared multiplied by this will give me a 3y squared I. And this is where we do the subtraction, just like our normal long division with numbers. So y cubed minus y cubed is a 0. Next will be my y squared over here. This is a no y squared minus a 3y squared. So that's a negative 3y squared I. Okay, and then 6y minus no linear terms. So that's just a positive 6y. And then next, I want to resolve the leftmost term, negative 3y squared I. How do I get this? I need to multiply by a negative 3yi. Negative 3yi times y will give me a negative 3y squared I. Okay, and then taking this negative 3yi times 3i, that is a negative 9y I squared. Negative 9y I squared. I squared is also equal to minus 1, so that's a positive 9y. So if I subtract, right, this is the same as this, so that's 0. Okay, 6y minus 9y is negative 3y. Bring down the next term. Okay, now I want to resolve negative 3y. I multiply by a negative 3, and this very nicely gives me no remainder. So that's when I know, right, negative 3i is a root of this one. If it's not a root, then I will get a remainder. And also, more importantly, this is my quadratic in y squared minus 3yi minus 3. So I hope that was a good revision on how to do long division polynomial. So I can re-express my f of y as this and my quadratic in y. Next, I want to know what are the two roots inside here. I'm going to use quadratic formula. Y equals to minus b plus minus square root of b squared minus 4ac over 2a. So just do that, and you'll get 3i plus minus square root 3 all divided by 2. So the other two roots are going to be 3i plus root 3 all over 2 and 3i minus root 3 all over 2. That is the answer for part 2. Now moving on to part 3. Part 3 says that, hey, let's go back to the question first. The question says that, hey, can you solve this equation? And this equation looks very familiar to this one from part 1. Right? If you look carefully at this one, and this is what we're given in part 3, this looks very similar to this if I let P equals to 3 and Q equals to 7 minus 9i. Correct? If I let P equals to 3, Q equals to 7 minus 9i. Yeah? So this is what we given in part 3. If I let P equals 3, Q equals 7 minus 9i. I've managed to transform the question in part 3 into the question in part 1. And then from the question in part 1, I know I can change it to another cubic polynomial that has no square terms. Right? I'm going to change it to the one with no square terms. Okay? And then from here, I'm going to actually substitute in the values of P, which is 3. Right? So this becomes 6y Q minus 7 times 27 over 27, so that's negative 7. So this 7 cancels out, and then I get this cubic polynomial over here. And this one looks familiar because this is our cubic polynomial in part 2. So from part 2, I already know the roots to this polynomial is negative 3i, 3i plus root 3 all over 2, 3i minus root 3 all over 2. The only problem here is we are not interested in y. We are actually interested in x. So remember the first substitution that we make, x equals to y minus p over 3. That is actually equals to y minus 1 because p is equals to 3. Okay, so if x equals to y minus 1, then x equals to y, which is negative 3i minus 1, 3i plus root 3 over 2 minus 1. So this is the 1 put onto the denominator 2, and then the other root is also the same. And that is the answer for question 9. As usual, you know I have skipped some steps. If you require clarifications, do let me know in the comments. Until then, I'll catch you in the next video.